Hello guys, George Kamiti here. In our previous lesson, we introduced portoflames analysis, and today we have a portoflame which is symmetrical and it is also symmetrically loaded. That means that it's two columns. Column AB as well as column DC are of the same length. That's why we are saying that it is symmetrical. It is also symmetrically loaded, meaning that this column and this one are carrying equal amounts of loads, and their reactions are also equal. So we are going to get or to calculate or to determine the reactions on this column as well as on this one. So if you are not yet a subscriber, please hit that subscription button. Very good. So the question of the day is we are supposed to analyze this portoflame using the moment distribution method and plot its bending moment diagram. Now, we are going to begin with the fixed end moment on the span BC. Therefore, the fixed end moment in the span BC. Since BC is the only member that is loaded, AB is a column, it is not loaded. DC is a column, it is also not loaded. Therefore, the fixing end moment at B, this joint here, will be given by negative WL squared divided by 12, since the beam is carrying a uniformly distributed load, so that is the formula. And this will be negative 2 multiplied by the span, which is 6 squared, and then we divide this by 12. And when we do so, we are going to get a fixed end moment of negative 6 kilonewtons meter. The fixing end moment at C will be given by positive WL squared divided by 12. In this case, fixing end moment at B is negative because it is an anti-clockwise moment. So the moment here will be anti-clockwise, but we are going to plot the free body diagram and see how we are going to distribute these moments. Fixing end moment at C is a clockwise moment. That is why it is denoted by a positive sign. So this is going to give us a positive 2 times 6 squared, divide this by 12, which is going to give us positive 6 kilonewtons meter. Then after determining the fixing end moments for span BC, the next thing we are going to determine, or the next step, will be determination of stiffness factors for members BA and BC. So the stiffness factors for BA and BC, we are going to begin with stiffness factor for member BA. This member here, this vertical column. And the stiffness factor will be given by 4EI divided by L, since the beam is fixed at A. So when a beam is fixed, that is the formula of determining the stiffness factor. And this will be given by 4E multiplied by I, which is just a single I, so EI divided by the span BA, which are 4 meters. So we divide that by 4, and that's going to give us EI. Then after determining the stiffness factor for member BA, we are going to determine the stiffness factor for member BC. Remember BC, which is the loaded beam. And the stiffness factor will be given by 4EI divided by the span L. The reason being, when we treat this beam as when we treat this portoframe as a continuous 3-span beam, the continuous beam will be continuous at C. And therefore, when we have a continuous section, the stiffness factor is given by this formula, 4EI divided by L. And this will be given by 4E multiplied by I, which is 3I. So we divide that by 3I all over the span, which is 6 meters B to C. And this is going to give us a 2EI. So that is the stiffness factor for that member. Then we need the summation of stiffness factor, which will be KBA plus KBC. And that's going to be EI plus 2EI, which will give us a total of 3EI. So that is the summation of stiffness factors. Now, after determining the values of stiffness factors for those two members, we are now going to determine their distribution factors. So we go to distribution factors for members BA as well as member BC. Now, starting with the distribution factor for member BA, we are going to have distribution factor for BA. This will be given by stiffness factor for member BA divided by the summation of stiffness factors. And this is going to be EI divided by 3EI. So the distribution factor for member BA is now going to be a that, since EI and EI are going to cancel out. Then we determine the distribution factor for member BC. And this will be given by stiffness factor for member BC divided by the summation of stiffness factors. This is going to be 2EI, which is the stiffness factor for member BA, divided by the summation of the stiffness factors, which is 3EI. And this is going to give us 2 over 3. From there, we need the stiffness factors for members CB as well as CD. Now, since this portoframe is symmetrical, then it means that the stiffness factor for member BA and that of member BC will be equal to stiffness factors for member CB as well as CD, since the portoframe is symmetrical. And that means that the distribution factors for members CB and CD are going to be as follows. Distribution factor for member CB will be equal to distribution factor for member CB will be equal to distribution factor for member BC, and that is 2/3. Likewise, distribution factor for member CD will be equivalent to the distribution factor for member BA. Therefore, BA and CB have got similar distribution factors, and that distribution factor is a 1/3. So, ladies and gentlemen, we now have all the values that we need for us to now plot the distribution table and carry out the distribution process. So, ladies and gentlemen, we are back again, and after we had calculated the stiffness factors, the distribution factors, the fixed end moments, the next step definitely will be filling or drawing a distribution table. I have already drawn it and filled everything just to save on time, yeah? But I'll explain everything, and I hope you are going to understand and to enjoy the content of the day. Now, on our portoframe, we got 4 joints. We got joint A, B, C, as well as D, and I have written each joint up there. That's the first thing we light on our distribution table. Then below the joints, we light the spans. Now, beginning with the joint A, we got the member AB written there. Joint B have got 2 members in total. We have member BA, which is on the left hand side, and we have member BC, which is on the right hand side of B. Joint C have got two members as well, member CB as well as CD. So we got CB and CD. Joint D have got one member DC, which we have written there. Then below the spans we got the distribution factors, and we have calculated them, and so that the distribution factor for member BA a third, that for member BC 2/3. On joint C, the distribution factor for member CB 2/3, CD a third. Then below the distribution factors, here comes the fixed end moments. Now, we only have a fixed end moment on member BC for joint B, since it is the only member that is loaded, and we calculated it, and so that the fixing end moment at joint B on member BC is -6. That one on member BA is 0 because member BA is not loaded. Likewise, on member C, we got the fixing end moment for member BC, which is +6.0. For member CD, 0 since it is not loaded. For DC, likewise, it is 0 since it ain't loaded. Then we go to distribution. So remember what we said about distribution. When we are distributing, we determine the excess moment that we have on a joint. For example, on joint B, on member BA we have +2. On member on joint B, on member BA we got 0 as the fixing end moment. On member BC we got -6.0 kN/m. So we have an excess moment of +6. Remember when we say that when we are determining the excess moment, we usually change the signs of the moment under consideration. So in this case, -6.0 will change to +6.0. Then we distribute on each member using its distribution factor. So on member BA, we are going to multiply this +6. After changing its sign, we multiply it by a third. That's going to give us +2.0. On member BC, we are going to have +6 multiplied by 2/3, which is +4.0. Then on joint C, on member CB, we got a fixing end moment of +6.0. On member CD, we got 0. Changing its sign to get the excess moment, this is going to be -6. So on member CB, we are going to distribute this -6 using the distribution factor of 2/3. So this is going to be 2/3 multiplied by -6, which is -4. On member CD, we got a third multiplied by -6, which is -2. Then on member DC, we got zeros. After distributing, that will be followed automatically by carrying over. So half of this +2 will be carried over from joint B to joint A, and remember the carryover factor is a half. So we are going to carry half of 2 to joint A, so that's going to be +1.0. Then from joint B we carry half of 4 to joint C, that is going to be +2.0. From joint C we carry half of -4 to joint B, that's going to be -2.0. Then from joint C we carry half of -2 to joint D, which will be -1.0. Then if you carry this one over, that will be 0, 0, and likewise that's going to be 0, 0. Then after that we distribute, and remember we are going to follow that procedure until we arrive at the required degree of precision. Therefore we are going to have all those steps: distribute, carry over, distribute, carry over, distribute, carry over, all the way. Very, very interesting, huh? So after carrying over, we are going to distribute. Here we got an excess moment of +2. Change the sign. So distribution on member BA, that will be a third multiplied by +2, that is +0.67. On member BC, +2 multiplied by 2/3, that is +1.33. On Joint C, we got a moment of -2. Distribute on member CB, that is 2/3 multiplied by -2, that is -1.33. A third of -2, that is -0.67. Then after distributing, we carry over. Half of 0.67 on joint B carried over to joint A, that is +0.34. Half of +1.33 on joint B will be carried over to joint C, that will be +0.67. Half of -1.33 will be carried over to joint B, which is going to be -0.67. Half of -0.67 will be carried over to joint D, that's going to be -0.34. After carrying over, what for us? Distribute. Excess moment here is +0.67. Change the negative sign to positive. Then distribute using the distribution factors. So a third of +0.67, that is +0.22. 2/3 of +0.67, that is +0.45. On joint C, we got a moment of -0.67. Change this positive sign to negative. Then distribute. -0.67 times 2/3, that is -0.45. -0.67 times a third, that is -0.22. Then after that, carry over. Half of 0.22 carried over to joint A, that is +0.11. Half of 0.45 carried over to joint C, that is +0.23. Half of -0.22 from joint C carried over to joint D, that is -0.11. Then distribute. We got an excess moment of +0.23. Change the negative sign to positive. So distribute. On member B, we are going to have a third of +0.23, which is +0.08. On member BC, we are going to have +0.23 times 2/3, that is +0.15. Coming to joint C, we got an excess moment of -0.23. Change the positive sign to negative. Distribute. On member CD, we are going to have 2/3 of -0.23, that is -0.15. On member CD, we got a third of -0.23, which is -0.08. Then after distributing, carry over. Carry over half of 0.08 to joint A, that's going to be +0.04. Carry over half of 0.15 from B to C, that's going to be +0.08. Carry over half of -0.15 to joint B, that's going to be -0.08. Then carry over half of -0.08 to joint D, that's going to be -0.04. After that, we distribute again. Excess moment, +0.08. Change the negative sign to positive. Distribute on member BA, a third of +0.08, that is +0.03. 2/3 of +0.08, that is +0.05. Coming to joint C, excess moment, -0.08. Change the positive sign to negative. Then distribute on member CB by 2/3 of -0.08, that is -0.05. On member CD, a third of -0.08, that is -0.03. Then after that, carry over. Half of +0.03 carried over from joint B to joint A, that is +0.02. Half of +0.05 from joint B carried all over to joint C, that is +0.03. Half of -0.05 carried over to joint B, that is -0.03. Then half of -0.03 carried over to joint D from C, that is -0.02. And then finally, we are almost getting to the required point of precision, or the required degree of precision. Therefore, the last thing we are going to do is to distribute. Remember, we cannot complete our table at the carry over point. We always complete it at the distribution point. So we distribute. On joint B, we got an excess moment of +0.03. Change the negative sign to positive. Then distribute on member BA a third of positive 0.03, that is positive 0.01, on member BC. 2/3 of positive 0.03, that is positive 0.02. Coming to joint C, excess moment, negative 0.03, change the positive sign to negative. Then distribute on member CB by 2/3 of negative 0.03, that is negative 0.02, on member CD, a third of negative 0.03, that is negative 0.01. Then the other parts are going to be 0. Then finally, we are now going to have the final moments. And for us to get the final moments, we are now going to add all the moments at each joint, at each member. So on member AB, joint A, we are going to have 1.0 plus 0.34 plus 0.11 plus 0.04 plus 0.02 to give us positive 1.5. And all the others, we are still going to do the same. Add all this moment, we get positive 3.0 on member BA. On member BC, from negative 6 all the way to positive 0.02, adding. So in this case, we are going to have minus 6 plus 4, minus 2 plus 1.33, minus 0.67 plus 0.45, minus 0.23 plus 0.15, minus 0.08 plus 0.05, minus 0.03 plus 0.03. We get to negative 3.0. Same case on joint C, member CB, positive 3.0 after adding all those moments. On member CD, negative 3.0, and on member DC, positive 1.5. Then here I have already plotted the free body diagram just to show how these moments are going to be just to show how these moments we are going to act on this portal frame. Are going to act on this portal frame. Now, before I explain what we got here, we have to calculate the vertical reactions. And as I said earlier, since this portal frame is symmetrical and it is symmetrically loaded, the column A, B, and DC will carry equivalent loads. So that means that they will share this uniformly distributed load equally. Now, for us to get the amount of load that each of these columns are going to carry, we are going to convert this UDL to point load. And we do that by taking the UDL, then multiplying it by the span over which it is distributed, that is B to C, which is 6 meters. So this is going to be 12 kilonewtons. And these 12 kilonewtons will act at the center of the beam B to C. So the column A will carry half of this load, which is 6 kilonewtons, as well as the column B. They will carry equal amounts of loads. Now, considering Newton's third law of motion, that states that for every action there must be an equal and opposite reaction. This total load carried by this column will be equivalent to the reaction at A. Therefore, reaction at A is 6 kilonewtons, and reaction at D, the vertical reaction at D, is also 6 kilonewtons, and that's what I have described up there. Good. Then we need what we call horizontal reactions, because of the external loads that are acting on these two columns to prevent sway or translation in any direction. Therefore, for us to get the horizontal reaction, for example, starting with the horizontal reaction at A, it will be given by the moment at A, which is 1.5, plus the moment at B, which is 3 kilonewton meter, divided by the span, that is A to B, which is 4 meters. And when we do so, we are going to get a horizontal reaction of 1.125 kilonewtons, which will also be equal to the horizontal reaction at D. Therefore, horizontal reaction at D is also 1.125 kilonewtons, and I have written them here on our free body diagram. So we got a horizontal reaction at A of 1.125 kilonewtons, and that one at D as well, 1.125 kilonewtons. The reaction at A as well as at D, 6 kilonewtons each. Then at joint A, we got a positive moment of 1.5 kilonewton meter, which is a clockwise moment. That is why it is positive. Then that one at B is on member BA, we got positive 3.0, which is also a clockwise moment. Remember I said that for us to be able to analyze a portoframe, we have to open it up and treat it as a continuous 3-spanning beam. Then on member BC, at joint B, we got negative 3.0 kilonewtons. That means that is an anti-clockwise moment. Then on member C to B, at joint C, we got positive 3.0 kilonewtons, meaning that that is a clockwise moment. Then on member CD, at joint C, we got negative 3.0 kilonewton meter, meaning that that is an anti-clockwise moment. At joint D, we got positive 1.5 kilonewton meter. Yeah, that is positive, meaning that it is a clockwise moment. Good. So that is the moment at D. So that's what we call a free body diagram. Then from there, we are now going to plot the bending moment diagram for this portoframe. And I have calculated here already the maximum bending moment for the span B to C. Remember, maximum bending moment for a member loaded with a UDL is given by WL squared divided by 8, which in this case, the W is 2 kilonewtons per meter, the span is 6 meters, therefore 6 squared, then we divide by 8, which gives us 9 kilonewton meters. So I'm now going to plot the bending moment diagram for this portoframe. Awesome, eh? Good. Good. Now plotting our bending moment diagram, we are going to begin with the bending moment due to vertical load, and that is a maximum bending moment for the span BC, which is 9 kilonewton meter. So since the member BC is loaded with a uniformly distributed load, the bending moment diagram due to vertical load is going to be a smooth curve. So the bending moment at B, that is 3 kilonewton meter, above that point. At C, we also have a 3 kilonewton meter, so on the same level as that moment at B. Then we join the moment at B with that at C. Good, so that's what we have. And this is going to be 3.0 kilonewtons meter, as well as the moment at C, 3.0 kilonewtons meter. Then on member, that is on member BC, negative 3, and on member CB, positive 3. For joint B, I have plotted the bending moment on member BC. For joint C, I have plotted the bending moment on member CB. Then on member BA, we got a moment of positive 3.0 kilonewtons, and on member AB, we got 1.5 kilonewton meter. So let me start with joint A, member AB. that is positive 1.5. So let me approximate 1.5 to be at that point. So that is 1.5 kilonewtons meter. Then on member BA, we got positive 3.0 kilonewtons meter. Let me approximate it to be at that point, double 1.5. So we are going to have that. So this is 3.0 kilonewtons meter. Then I'm going to join 3.0 kilonewton meter to 1.5 kilonewton meter. Let me hope I'll be able to measure correctly. Yeah, that was a good try. Coming to member CD. So on member CD, this one is member CB. On member CD, we got negative 3.0 kilonewtons meter. So let me approximate it somewhere there, equivalent to this one on the left hand side. So this is 3.0 kilonewtons meter. Then on joint D, member DC, we got positive 1.5 kilonewtons meter. So positive 1.5, about that point. So we join that there, and then we write there 1.5 kNm. And then we join the 3.0 kilonewtons meter to the 1.5 kilonewton meters down there. We're almost, but at long last, we have been able to accomplish the mission. So let me rewrite my 1.5 kilonewtons meter. Spread it a bit. 1.5 kNm. Yep. So that's what we got. 1.5 kilonewton meter here. It is positive, so this is a positive moment. 3.0 kilonewton meter, that is a negative moment. This one is negative. That one is positive, negative, and then this one is negative. This one is negative, and this is positive moment. So this is now what we call the BMD for such a portal frame. Then I'm going to shade off the outline of my bending moment diagram so that it becomes clear, visible, smart, beautiful, etc, etc, etc. So guys, that's how we shade off the outline of our bending moment diagram. And please keep on subscribing, comment, like, share our video to your friends, and please give us positive comments. So that's our bending moment diagram for a symmetrical, simple portal frame. So we thank you for watching our video, and let's meet in yet another lesson, God willing.